All right, hello. I'm back. Sorry I got interrupted, but what we were doing before I stopped was we were breaking these this component of the weight into the parallel and perpendicular components along the x and y axes. And I'm drawing my second free body diagram just so I have all the broken down components that I can add to each other. So as we had before, we have the force applied here. We have the I'll write it down here actually. FGY, the y component of the gravity, and we also have FGX, the x component of the gravity. Now, how are we actually going to get values for FGY and FGX? Well, we look at this triangle here, then draw it over here so it's a little clearer, and we recognize that this is just a right triangle. I'm sorry, I drew that at an improper angle. I try to mimic the angle it was at previously. So like I said, it's just a right triangle, and keep in mind that the overall vector that we're trying to break down, that's always going to be the hypotenuse. And we're breaking it down into parallel and perpendicular components along the x and y axes, which make up the two legs of the triangle. So this is FGX, and this is FGY. Now, if you remember our trig functions, and also label that theta. Sorry, that's something I should have done way back there. Even back in the original diagram, I can angle this theta. So what I'm saying here is that this angle is exactly the same as the angle of elevation. So I'm giving it the same name. All right, back to our triangle. Remember, cosine of theta equals opposite over hypotenuse. So cosine of theta then adjacent over hypotenuse. So cosine of theta then is equal to the adjacent leg of the triangle next to the angle, which is FGY, over the hypotenuse, which is just FG, the total vector, the vector we started with, the weight. So FGY is just equal to FG cosine of theta. Similarly, we go with sine of theta equals, this time it equals opposite over hypotenuse. So the opposite leg of the triangle, opposite from the angle theta, is FGX, and the hypotenuse, as usual, is just FG, the original vector we started with. So then we can say FGX equals FG sine of theta. And I can write these on our graph if we want to do that. Or our free body diagram, excuse me. FG sine of theta, FGY equals FG cosine of theta. And I'll just kind of box this out so it doesn't get mixed up with anything else. So now we just have four vectors that need to be added: FGY, Y, FGX, and FA. So I'll go back to my chart here. In the x direction, FGX, we saw it down here, FG sine of theta, that is positive, just because we choose the positive x direction to be to the right down the incline, this way. Sine of theta. Now we also have the other force, which is the force applied. That is in the negative x direction. So I'm going to put a negative there. And we know that the crate is held at rest, so it's not moving. So AX must equal 0. So when we sum all these forces, they're equal to mass times acceleration in the x direction, as usual, but that's going to equal 0. In the y direction, we have the normal force, which is positive, and we also have this component of the weight, FGY, and that is going to be negative. So we have negative FGY equals negative FG cosine theta. Now, in the y direction, is the crate moving at all? Well, no, it's not moving at all because it's not sinking or it's not floating. So that means the sum of the forces equals MAY as usual, and that equals 0. Okay, so if I were to sum all my forces, sum of the forces in the x direction equals FG sine of theta minus FA, and that equals 0. In the y direction, Fy equals Fn minus Fg cosine of theta, and that also equals 0. And we're after the normal force, so Fn equals Fg cosine of theta. So we're actually done because the problem's asking for the normal force. We have an expression for that, and you can plug in Fn is just equal to 25 newtons times the cosine of 25 degrees. And then you can calculate that out. Okay, there are people wanting to get in this room, so I'll move rather quickly on this problem. We have a 6 Newton force that acts horizontally on a 10 Newton block. This is force of gravity, and it's horizontally, that is initially at rest on a horizontal surface. The coefficient of static friction we have, while the coefficient of kinetic friction we also have, was the magnitude of the frictional force that acts on the block. So force applied equals 6.0 newtons. Force of gravity equals 10 newtons. We could say V0 equals 0. And we want to find the frictional force. Drawing the diagram, we have force applied. We have force of friction that always opposes motion. We have the force of gravity. And we have the normal force. If I'm to then draw a free body diagram, force of gravity, normal force, force applied, and the force of friction. Real simple diagram because all of our forces are already parallel or perpendicular to each other. So back to the chart, summing up the forces in the x direction. You have the force applied and you have negative force of friction, and the block is initially at rest, but we don't know if there's an acceleration right now because we have to find out if the block moves or not. In the y direction, we have the normal force and we have negative force of gravity, and this equals MAY, which does equal 0 because there's no movement in this dimension. There's only possible movement in that dimension. So summing up our forces in the x direction, FA minus the force of friction equals MAX, and this is true, we just don't know if acceleration equals 0 yet. And Fy equals Fn minus Fg equals 0. Normal force equals the force of gravity. That's an important thing. I shouldn't box it, it's not the final answer, but that's an important thing to know, and that's not always going to be true. If I were to have a force coming down at an angle or something, the normal force would not equal the force of gravity. It would be increased. But in this case, it is true. So first, determine if there is motion, and we do that by calculating the maximum force of static friction. And if you remember just the definition of that, mu s times Fn, but now we know Fn equals the force of gravity, so mu s equals Fg equals, I should have written down here with our knowns, equals 0.50 times the force of gravity, which is 10 newtons. So the force of static max equals 5 newtons, right? And we also know that the force applied is greater than the maximum force that static friction can apply. So there is motion. Now, since there is motion, if you remember that graph that I showed you in class, very important graph, as you give more applied force, the friction increases up to a point which is Fs max, at which case the force of friction decreases and assumes a constant level. That constant level is the force of kinetic friction. So since the object is moving, we know that the force of friction equals force of kinetic friction, which equals mu k times Fn, but again, we know that Fn equals weight, mu k Fg, so that equals 0.30 times 10.0 newtons, and the force of friction equals 3.0 newtons. Okay? And it doesn't matter how much more applied force you apply. If you have a 10 Newton applied force, your force of friction is still going to be 3 newtons because it's kinetic friction. If you were in this regime, like if the object were not moving, no motion here, then the force of friction would equal whatever force applied you apply to the object. So if you applied a 3 Newton force, your force of friction would be 3 newtons because it would have to be enough to cancel out that applied force and prevent motion. Okay, so we are done with the first practice exam.